Okay, this is a screencast showing an example of calculating steady state error for a control system problem. Okay, so in this particular problem we have something that's set up in a usual form where you have to identify the components, and so if you're looking at this would be the G of S, and this part would be H of S. And we're asked to calculate several things. The first thing is the closed loop transfer function. So that would be Y of S over R of S. And we know that's going to be G over 1 plus GH. And so we have these things that we can plug in. 3 over S plus 2. 6S over S plus 7. And then on the bottom, 1 plus, all these things multiplied together. So there's that. We could simplify that, but really there's not a point to simplifying it. So we're going to move on. Next, I want to tell you about the steady state error, and to get to the steady state error we need the error signal transfer function. Okay, so we derived this in class, and it turns out that if you have this general form where you have a G in the feed forward loop and then in the feedback loop you have H, then the error transfer function E over R is going to be 1 over 1 plus GH. Okay, so let's put a box around that. Let's color it in, because this should go in your formula sheet. You don't want to have to rederive this on an exam. Okay? So, in part A, part C, we asked for the steady state error for a step of amplitude 3. Okay, so what that means is that we have R of S is 3 over S. Okay, so we can get to steady state error by looking at the limit as S goes to 0 of S E of S. Remember, that's the final value theorem for the error signal. Okay, and so plugging this in, we look at this transfer function. We know that E of S is going to be S times R over 1 plus GH. Okay, and we know what R is. All right, so when we plug in, we get limit as S goes to 0 of 3 over S times S over 1 plus GH. Okay, so the S's cancel. And I can just plug into 1 plus GH in the denominator. Okay, so when I look at GH, okay, that was this term. I'm just going to grab this here. Okay. All right, so this is equal to limit S goes to 0 of 3. The 3 is left over from here. And this is what we have. Okay, so I can plug in that limit. All right, so what do I get? Well, it's going to be a 3 on the top. I have a 1 plus. And then when I plug in 0, I get 4 over 6 and 3 over 2 and 6 times 0 over 7. So that term is 0. Okay, and so because that term is 0, That knocks out all this other stuff, and we get a steady state error of 3. Okay? Hopefully that makes some sense. All right. Now, what happens if, let me move this to the side. Now what happens if we do essentially the same thing, only this time in part D, R of S is a ramp function of slope 4. Okay? So the Laplace transform of a ramp is the slope divided by S squared. So that's what we have for R of S. Okay? So E of S is going to be E steady state error, it's going to be the limit as S goes to 0 of S times 4 over S squared divided by 1 plus GH. Okay, so you see here, one of the S's cancels, but I get a free S in the denominator. Okay, so that's going to be limit as S goes to 0. Let me paste this back in. That's in the denominator. Okay, this is a 4 up on the top. And remember, we had this free S right here. And so that's going to show up there. Okay, so there's that S. All right, so what happens? What happens is you get division by 0. You know, when you plug in S equals 0 into all these terms, you get something finite here. That one's 0, but 0 times essentially 1 is 0, and so as S goes to 0, this goes to infinity. And we knew that if you had a finite steady state error from a step, then you're not going to be able to track a ramp with finite error. Okay, so that's how you do that type of problem.